Welcome to day 3 of our differentiation unit. Today we will be putting the power law that you practiced last lesson into practice, and we're going to be looking a little bit at tangents and normals. We will discuss what we mean by a normal line if you haven't come across that before. I'm sure you're familiar with the idea of a tangent. First of all, here's the starter. Find the equation of the line passing through the point 3, 4 and 5, 8. So something that you will have looked at in grade 8, it's just a bit of a review, and it obviously links to what we're doing today. So if we want the equation of a straight line, we need the line's gradient and we need a point on the line. So we've been provided with 2 points, but we haven't been provided with the gradient, so we'll have to find that out first of all. So we'll just do the change in the y coordinates divided by the change in the x coordinates to find that. So that is 4 over 2. So our slope is 2. To find the equation of our line, we've got a couple of options. We can use y equals mx plus b and substitute in for m, and use one of our points to substitute in for y and x to find out what b is. Or you may have come across this form, where once again we substitute in for m as our slope, and x1 and y1 are one of our points that we can use. Both of these will give you the equation of the line. I'm going to use the version on the right, so I've got y minus, I think I'm going to pick this coordinate as it has slightly smaller numbers to deal with. Our slope was 2, x minus 3. Okay, this is actually the equation of a line as it is. I'm going to be a bit more thorough and I will tidy it all up. So y minus 4, okay, and then I will move that 4 over to this side. So there we go, there is my equation of a line. I could obviously check this on my calculator. I could put this in as my function and go to the table. I guess would probably be the easiest way of checking to see that those are there. Okay, so that's the starter. Let's move on now to the rest of the lesson. So let's take a look at an example of this. We're finding the equation for the tangent to the curve y equals 2x squared plus 4 root x at the point where x equals 4. So let's take a quick look at this on the calculator. I've put in our function, which looks like this. Let's just zoom out quite a lot, I think, in the y direction. So let's go down to -10, and maybe we'll go up to 50 and take a look at that. Okay, so this is where we're looking at. Oh no, here's where we're looking at. And in fact, we can get if we go to 4, we can get our calculator to draw in the function. So that's what we're looking at. Quite a steep gradient. Remember, we're going up to 50 here, and we're only going along to about 5 or 6 there. So quite a steep function, quite a steep slope, and I'm clearly going to have a negative y-intercept. Okay, so if I want to find the equation of this tangent, I need to know the slope of the tangent, and I need to know a point it goes through. So to get the slope, the easiest way is to find the slope of our function when x equals 4. It has to be when x equals 4 because that's where the function and the tangent are meeting. So that's the point where the tangent slope is equal to the function slope. So I'm ready at 4, good. So if I find the slope, there we go, the slope is 17. So when x equals 4, dy by dx equals 17. Notice we haven't even actually had to differentiate this function in order to find the slope. Obviously, you looked at the power law last lesson, so you'd be able to do that. We'd think about this as 4x to the power of a half, and we'd be going through multiplying by the power and reducing the power by 1, and then substituting in 4. That's clearly not the most efficient way of doing that, is it? This using a calculator is. So now I've got the slope of my tangent, I need to find a point it goes through. And the easiest point is where it meets our equation, where it meets our curve. And the reason why that's an easy place to find is because we can get the y value from it. So as long as we go to the point where they're meeting, which I'm doing, if I hit menu, it clears out all of those options, and I can see when x is 4, the y value is 40. So a point that our function goes through is 440. So let's find the equation of the tangent. Let's just say what we're doing here, tangent. Okay, I'm going to use the other version of the other way of finding our equation just to mix that up. Let's give ourselves a bit more space. So my y coordinate is 40, m is 17, x is 4, plus b. Okay, so 17 times 4 is 68. 40 minus 68 is negative 28. So that's my b value. So y equals 17x minus 28. We have found the equation of the tangent at the point when x equals 4. Please note there was a typo in the completed class notes. The m value in the equation should be 17, not 4. Okay, let's take a look at the second example. We're looking at the side of a hill being modelled by this function. Using technology, sketch the graph. So we should have that here. Let's just check negative 0.02x squared and 3.4x. And we need to set a window. I've had a bit of a play around. So I think this should be roughly where we need to go. I'm not sure quite how high it needs to be. Let's try that. Okay, that's not too bad. So if I'm doing a sketch, I should probably put in some information. It'd be good to know roughly where this x-intercept is. So onto root, it's at 170. And it'd be good to know where the top is. So 85, 144.5. Okay, so I'm going to try and put that information in a little sketch now. Let's have this. This is going to be interesting. Let's see how this goes. So there we go. So this I think was 170. This was 0, and that was 85, 144.5. 85, 144.5. Okay, we've got y, we've got x. Okay, I think that's all right as a sketch. There is a research station on the hill at the point where x equals 50, so somewhere kind of around here, I guess. The scientists in the research station need to have a direct line to an observer on the ground. Find the minimum distance to the nearest meter from the foot of the hill at which the observer could reach the research station. So if we want a direct line, let's just extend my x-axis out a bit further. We're looking at having a tangent, aren't we? That's going to be the closest. If I go closer, the hill's going to get in the way. If we go further out, it's not the minimum distance. So we're going to need to find this tangent, and then the distance we're after is here. I'm making an assumption here that the bottom of the hill is at when y equals 0. Okay, so the x-axis is our ground. That's the assumption I'm making here. So I would like to find the equation of this tangent. I think then I would be able to find its y-intercept and get this distance along here. Okay, so that's my plan going into this question. So finding the y-intercept is my first job. Finding the equation of the tangent is my first job. So just as before, we need a slope and we need a coordinate for that. So let's go back to our graph. We want to go to 50 now, because that's where the scientists are. Oops. Okay. Must have had some other things typed in there already. Okay, go to 50. So the y coordinate is 120, 50, 120 at that point, and we would like a slope. There we go, the slope is 1.4. Let's just check we're still on 50, yeah. It's very easy, especially when you're using your calculator and you're playing around with these buttons, to nudge the graph and to just kind of move off where you think you can be. And if it doesn't move a lot, it's easy to end up with a very different, to be finding values at a very different point to where you want to. So if you're doing a few things at x equals 50, once you've finished, it's worth just checking, am I still at x equals 50? Yes, I am. So back to the question. My slope was 1.4. So for our tangent m equals 1.4, and we're going through 50, 120. Okay, so y equals mx plus b, 120, 1.4 times 50 plus b, and so b equals 120 minus 1.4 times 50. Okay, so b is 50. Let's just take a look at that. Does that look sensible? Here's 120. Yep, that looks reasonable to me. So b equals 50. So my tangent line is y equals 1.4x plus 50. Okay, thinking back to the question, I haven't found the answer yet. I found the equation of this line. So now I want to find this point here, which is the y-intercept. No, it's not, it's the x-intercept. But we are going to make y equals 0. So let's say when y equals 0, okay, so to find x, I'm going to do negative 50 divided by 1.4. Which might not be a very nice number, or it might not be a very clean decimal, but that's what we need. 35.7 we'll write down for now. Negative 35.7, because I should have had negative 50 and I didn't. Okay, so this point up here is negative 35.7. Find the minimum distance to the nearest meter from the foot of the hill at which the observer could see the research station. So this distance is, this is the foot of our hill we've assumed. So the minimum distance to the nearest meter is 36 meters. So far we've looked at tangent lines. We're now going to talk about the idea of a normal line. And really this is just a bit of vocabulary. So in this little diagram here, we've got a red curve, which is our function. We have a green line that is a tangent to this curve at this point. And the normal line is one that is at 90 degrees to the curve and to the tangent. So it's the same idea that it goes through a point of the curve, but this time it's perpendicular to the curve rather than at the same slope. And obviously you've looked at perpendicular lines before. Oops, let's just get rid of that. You've looked at perpendicular lines before, so you know that if they're perpendicular, their gradients will have a product of -1. So you're going to find the negative reciprocal of the tangent slope, and it will be the slope of the normal. So let's take a look at a couple of examples doing that. If you're feeling confident with that, I would have a quick go at question 3 and you may not need to listen to this. So we're going to find the equation of the normal to the curve of this function at the point when x equals 1. We're going to go through a very similar process to what we've been doing to find the equation of the tangent. The only thing we have to do is to find the normal slope from the tangent slope. So just as before, we would like a slope and we'd like a point. Let's get the calculator, and we're going to go back here, and we're going to put in our new function, 2x cubed plus 3x minus 2 plus 3x minus 2. Okay, I had we don't want to be going up to 200 anymore. I'm not exactly sure what we want to be going up to, but let's just start with this. Okay, that's not ideal, but it will do because we've got x equals 1 over here. Okay, so let's go to 1. Okay, so it goes through the point 1, 3. That's useful. Let's write that down. So we're going to go. I'm going to just put that over there for now, because I think really we need to be thinking about the slope first of all. So slope. The slope of the curve is 9 at that point. Let's just check. We're still on 1. Yep. Okay. So the tangent at x equals 1 has slope 9. Okay, so if I want to find the normal, the slope of the normal will be the inverse reciprocal of that, so it will be -1/9. And we have this point that we're going through, 1, 3. Okay. I have not found a way of getting the calculator to sketch the normal, but if we put on the tangent line, so we can see it's this dashed line, so our normal slope is going to be somewhere over here. So you see a very fairly small negative slope, which seems about right, and we're going to hopefully get a y-intercept that's kind of somewhere between 3 and 4, but probably closest to 3. Right, I think it's just the same as before really, with finding an equation of a line now. So y equals mx plus b, I'm going to go straight for 3 equals 1/9 times 1 plus b. So b is 3 and 1/9. Okay, and just to finish this off, the equation of my normal, y equals a -9th x plus, you could write it as 3 1/9 or 28/9. There we go. So our final example is more challenging. We have a gradient of the normal to a function of this equation at the point 1b is -1/4. That is a very dense, densely packed sentence. So basically we're saying that we've got a function, we've drawn a normal at a certain point to it, and we've found that the gradient of that normal is a -1/4. We've got a couple of unknowns here, so we're not going to be able to rely on our calculator so much. We're going to have to use a bit more of our algebra as we go along. So if we were wanting to find the gradient of the normal, or the equation of the normal, we'd be able to do that given a function and a point. And the things we'd do is we'd find the gradient function, we'd find the derivative, f prime of x. So we'd use our power rule, we'd multiply by the power, we'd reduce the power by 1, we'd get 2x would go to 2, and the constant would go to 0. Okay, and we'd have the point that this is all happening at, which is x equals 1. We could substitute 1 in, and we'd get this. And this would give us the slope of the tangent. And from that we'd do the negative reciprocal to get the slope of the normal. So if we know the slope of the normal is -1/4, we know the slope of the tangent must have been 4. So when we found the derivative, substituted in 1, we would have got the answer 4. So 4 must be equal to 3k minus 2. So what we've done here, we've found the gradient function, we've substituted in x equals 1, which is where this normal is happening, and we know that that would give us the slope of the tangent. So we've said that that must equal the slope of the tangent, which is the negative reciprocal of the normal slope. And from this we can solve it and we can get one of our unknowns, we can get k. So let's add on 2 and let's divide by 3. K equals 2. Right, next, how are we going to get b? Well, if we've got our normal, it's meeting our curve at this point 1b. So the way we'd find the y coordinate is we'd just substitute in the value 1. So k times, well, actually no, k as well, so that's 2 times 1 minus 2 times 1 plus 1. And that should equal b, shouldn't it? That should be our y value. So b is equal to 2 minus 2 plus 1. B is just 1. Okay. Not so challenging from an arithmetic point of view, but from an understanding and being able to break down the question point of view, this was a bit more challenging. The way I thought about it was, rather than thinking about all this information they gave me, I imagined a more standard question. And a standard question is, what is the equation of the normal given a function at a certain value of x? And I thought, well, what processes would I go through? I'd find a gradient function and find out what the slope of the tangent is, and then the normal, and that allowed me to get one of the unknowns. And the second thing I'd be looking for would be a point that the normal goes through, and we'd do that by using our function. Okay, you can see down here is the work for Friday's lesson. Please join the team's conversation if you have questions about that. Good luck.